Yes, does anyone has any doubt?
In an example, there is that X bar is asymptotically efficient, and you introduced a new variable that delta n x bar if mod x bar greater than equal to 1 by n to the power 1 by 4.
Which example is this?
Mm, x1, x2, xn IID normal theta 1
Right.
to estimate theta,
Huh.
so that x bar is asymptotically efficient, and then delta n x equal to x bar if mod x bar greater than equal to 1 by n to the power 1 by 4, and ax bar
Acha, that
if
example
mod.
you're talking about. Let me
This,
see.
this is from actually week 9, module 44, first example.
Uh, uh, okay. This one, this one example, right? Is that okay?
Sir, can you share your screen?
Okay. Let me do that first. Can you see it now?
Uh, yes, sir.
Yes, sir.
So here in this example, for the
This example,
le-
in the light of the last examples, it says there exists estimators delta n for which this goes to non-zero, but v theta is greater than or equal to 0, getting violated at some thetas. Such thetas have Lebesgue measure 0, called points of superefficiency. For example, if you look at this result, uh, it says that x1, x2, xn be IID with PDF and PMF f theta x. Suppose these conditions are satisfied, which would be the case in exponential family normally, and double derivative of density is bounded, and delta n be any efficient estimator such that this happens, then he says v theta, if delta n is any estimator such that this goes to normal 0 v theta, then v theta would always be greater than or equal to g prime theta whole square upon I theta, except on a set of Lebesgue measure 0. That means except for few points, and the set of such point cannot contain any interval, this would always be satisfied, right? So this may get violated, for example, at 1 point, at 2 point, at countable number of points. But wherever it will get violated, that set will have a Lebesgue measure 0. That is what it is saying. So v theta will always be greater than or equal to g prime theta by whole square by I theta for every theta except on a set of Lebesgue measure 0. Now he says you might have this, and this may not hold for every theta. So at some theta, it may get violated. And that is what
violated means for some theta, v of theta less than g dash theta whole square by I theta.
right. But
Oh,
set of all those thetas would have a Lebesgue measure 0, right?
okay.
There'll be only few points of that kind. So such a set will have a Lebesgue measure 0. So that is what I am showing over here, x1, x2, xn normal theta 1, root n. If I look at g prime theta by whole square by I theta, that turns out to be 1, which is same as the variance of x bar. So x bar is asymptotically efficient, right? By definition, because I had said any estimator for which this bound is attained, we call such a estimator to be
Asymptotically efficient.
asymptotically efficient. So x bar is asymptotically efficient. What he says is, I'll show that there'll be an estimator where root n delta x bar minus g minus theta goes to normal 0 v theta, but v theta may not be greater than or equal to this at some thetas, right? That is what I'm trying to show. So I'm trying to look at this example. Delta n is x bar if mod of x bar is greater than or equal to 1.4, and ax bar if x bar is less than 1.4. Now note that this estimator is almost same as x bar, at least intuitively it looks like, because as n goes to infinity, this set would be almost zero. So that is what I try to show. So I try to show that what is the probability that root n delta n minus theta less than or equal to x, which was the asymptotic distribution of x bar also. So I consider two cases. So in the case theta not equal to 0, it goes to phi x. And in the case theta is equal to 0, it goes to phi of x by a. Right? So that means asymptotic distribution is always normal. When theta is not equal to 0, mean is 0, and that is what it is said. So v theta is 1 if theta not equal to 0, and a square if theta is equal to 0. Because it is a normal 0, a square. Right? This is a distribution of normal 0, a square. Is that okay?
Okay.
So my v theta is 1 if theta not equal to 0, and a square if theta not equal to theta. Now a is in my hand. Right? So for a less than 1, you can see that v theta is always less than 1. Right? Right? So that v theta greater than or equal to g prime theta whole square by I theta. But set of all those points is only single point, theta is equal to 0. And Lebesgue measure of the set theta is equal to 0 is 0 because it is a singleton. Is that okay?
Okay.
Yeah. So what this example is trying to show is there may exist thetas where v theta greater than or equal to g prime theta whole square by I theta and may not hold. But the set of all those thetas where such an inequality does not hold will have a Lebesgue measure 0. Or in other words, such a set cannot contain any interval. So for example, there was only one point, theta is equal to 0. Theta is equal to 0 does not contain, it is a singleton, so it cannot contain any intervals, so its Lebesgue measure is 0. Okay. So at some thetas, it may get violated. That is what last example. Yeah.
Okay, sir.
Yes, any other doubt anybody has? Let me minimize this.
Sir, I have a doubt. In that case, where theta is not equal to 0, you are showing that probability that x bar mod of x bar converges in probability to mod of theta, right?
Which one?
In that case where the theta is not equal to 0, that way.
Same example, no?
Just 1 second. Yes, sir. Yes, sir. The same example where x1, x2.
So let us
That a.
So
Yes, yes. This example
theta
only.
not equal to 0, right? Yeah. Yeah. So
So after that, you are showing that probability that x bar is less than 1 by n to the power 4 is tending to 0 as n tends to infinity. Can you explain just that portion once?
let us look at probability mod of x bar is less than 1 upon n by 4. This is same as probability that x bar is greater than 1 upon n by 4, less than 1 upon n power 4. Right?
Yes.
Now, when theta is not equal to 0, I know that I normalize it because root n x bar minus theta is normal 0, 1. Right? So I just convert this into standard normal the way you do it in your BSc and other things, right? So it is root n because x bar has a variance root n 1 upon n to power 1 by 4 minus theta, right? Minus phi of root n minus 1 by n to power 4 minus theta, right? This is what it is, right? Because x bar is normal theta 1 by n. So I've converted this probability into a normal 0, 1, right? By subtracting it by theta and dividing. Now let us look at what happens. First case, consider theta less than 0, right? If theta is less than 0, then root n theta, root n into 1 upon n to power 4 will anyway go to infinity. So first of all, if theta is less than 0, this quantity is positive.
Yes, sir.
So where does this will go to if theta is less than 0? Yeah. if theta is less than 0, let us look at this whole quantity, right? What is this? This is n to power 1 by 4 minus root n theta. So if theta is less than 0, where would it go, the quantity go to?
Infinity, sir.
Huh?
Infinity.
Why?
Hello, sir.
Yeah.
Can you repeat the question again?
My question. Suppose theta is less than 0, right? Where does this quantity goes to?
So this quantity so goes to
Infinity, sir.
infinity, sir.
This quantity will go to
Infinity.
So this would go to 1, right? And what about this?
Fi-
What about this?
Same.
Same, right? So 5, 1, 5, 1, 1 is 0. Is it okay? Similarly, for theta greater than 0, you will look at it. Is that okay? For
yes,
theta
yes.
0, where does this go to?
For theta greater than 0, it should go to minus infinity.
5
Then
minus infinity is
it
0.
would.
This also goes to this thing, so this is also 0. In either case, it is 0. So it is going to 0. Otherwise,
Yes, yes.
also you can look at when theta is not equal to 0, right? Theta is not equal to 0, then you know that x bar is consistent for theta. So x bar will go in probability to theta.
Yes, sir. Yes, sir.
That means in probability x bar would be very near theta, right? But theta is different from 0, and x bar is near theta. So that means x bar would be away from 0, because x bar goes in probability to theta.
Yes, yes.
Theta is different from. And what is this? This is a probability saying that when n is large, this is that x bar is very close to 0, which may not happen. So intuitively also it looks like this will go to 0, right?
Okay, sir. Okay, sir. Yeah.
Otherwise you can get it like this. Yeah. Any other doubt?
Sir, in assignment number five, problem 1, I have
Anything, anybody wants to ask something in lecture notes? First, let us finish lecture notes and then we can go to the assignments. I think that would be better.
okay, sir.
Anybody having a doubt in the lecture notes?
So in the last example, that x1, x2, xn I normal theta 1,
Right.
and then there is delta n 2x equal to 1 by n summation indicator of xi less than equal to mu naught.
Which example?
Last example of before MME estimation.
Just before MME estimation, right? Okay, let me see. This example? Normal theta 1, g theta is probability x1 less than or equal to u naught?
Yes, sir.
Yeah. So what is
So,
the...
sir, here how the
I
ARE
told you there is some problem over here. You have to slightly modify this one. So what I am doing is you are estimating phi of u naught minus theta, right? So which is same as delta n1 is phi of root n by n minus 1 u naught minus x bar. So I have to write down this as h of cn times sample mean, right? Now u naught minus x bar is not a sample mean as it is. So I have to convert it. So what I do is I write down ti as u naught minus xi, right? Ti as u naught minus xi. So this example as such, the way it is written over here is not exactly correct. So I'm telling you how to modify this example. This you should not follow as it is the way it is written over here. So what I'm saying is, because I have to write down this as h of cn x bar, cn is already there, root n upon n minus 1. So I have to write down this as a sample mean of something. can be written as a sample mean of something only when I define Ti as U0 minus Xi. If I define Ti as U0 minus Xi, then T bar is nothing but U0 minus X bar. And then it can be written as phi of root of n upon n minus 1 of T bar, which is phi of Cn T bar. So H I can take as phi of X only, right? That is the whole idea. So I define Ti as U0 minus Xi, then T1, T2, Tn are IID with mean as U0 minus theta and variance as 1. Okay. And delta N1 is nothing but H of Cn T bar, where Hx is nothing but phi of T. Is that okay? Actually, here anyway, you are asking just to find so here it is saying you to consider Hx as U0 minus X bar. So then root n X bar minus theta goes in distribution to normal 0, 1. If I consider Hx to be phi of U0 minus. So I should consider here actually because H of Cn X bar. So that I should, so if you do that again, you will get this thing only, right? I'm saying rather than applying this directly on U0 minus X bar, apply on T bar, right? Then root n H of, what I know is root n T bar minus, what is the mean of T bar? U0 minus
U theta.
goes in distribution to normal 0, 1. Is that okay? Root n T bar minus U0 minus theta goes into. So that means root n of, here Cn is root n upon n minus 1, which is same as 1 minus 1 by n to power minus half, which is same as 1 minus 1 by 2n, right? Right. So that means root n H of Cn T bar minus H of theta. H of theta here is H of U0 minus theta because Ti's have a mean U0 minus theta, right? So H of U0 minus theta would go to H prime theta. That means H prime of U0 minus theta into Z, which is normal 0, 1. Now what is the H over here? Phi, capital phi T. So H prime T is small phi T, right? So this becomes phi of U0 minus theta. So phi of U0 minus theta into normal 0, 1 will be normal 0 phi square U0 minus theta. And this is nothing but root n. H of Cn T bar is nothing but delta N1 minus phi of U0 minus theta. So this would be capital phi of U0 minus theta. Right? So that is what it is. Is that okay? Exactly follows the same way. Some modification is required as it is. And delta N2 is clear because delta N2 is just a mean of Bernoulli random variables. I xi less than or equal to U0 is a Bernoulli distribution. It takes only two values, 1 and 0. With probability of success is probability x1 less than or equal to U0, which is phi of U0 minus theta. So root n delta N2 minus theta goes to normal 0 theta. So this is what it is turns out to be. Is that okay? So final answer is correct, except that small modification here would be required in terms of U0 minus X bar. You don't consider U0 minus X bar. Define Ti as U0 minus Xi. Then delta n can be written as phi of root n upon n minus 1 T bar, which is H of Cn T bar. Right? And then you use the delta method which we use for H of Cn T bar. Is that okay?
Okay.
Yeah.
Sir, here ARE, how the ARE is here increasing function of mu naught minus theta?
That you can prove.
Oh,
Right. That you try to prove.
okay.
First of all, note that it is a symmetric function of U0 minus theta. Right. In place of U0 minus theta, if you put theta minus U0, it remains the same. Right. Right. So basically what you need to show is phi square x upon capital phi x into 1 minus phi x is an increasing function of x. For x greater than 0. For x greater than 0.
Oh, x.
Right. Phi square x divided by phi x into 1 minus phi x is the increasing function of x for x greater than 0. Take the derivative and try to do that. It will, you can show that. Is that okay?
Okay.
It will be slightly involved exercise, but it can be shown. Otherwise, you can plot it also. Try to plot phi square x upon phi of x into 1 minus phi x for x greater than 0. It would be increasing. And it is symmetric because phi square of x is same as phi square of minus x. And if you put minus x over here, I get 1 minus phi of x over here. If I put minus x over here, I get this. So this is symmetric in u naught minus theta, right? Means you only need to know that it is an increasing function of mod of u naught minus theta. So that is equivalent to saying that phi square x upon capital phi x into 1 minus phi of x is an increasing function of x for x greater than 0. Is that okay? So that you can show analytically, as well as if you want, you can quickly go to Excel sheet and then plot a graph of this function using any software, and you'll see that it turns out to be increasing. Yeah. Any other doubt anybody has?
Sir,
Yeah.
sir, if delta nx is a consistent estimator, then limit n tends to infinity. Expectation of delta nx is equals to g theta, and variance is tends to 0 as n tends to infinity. So can you give an example of an estimator which does not follow this condition, but it is also an consistent estimator?
No, first of all, that condition requires existence of a movement, right?
Yes.
That condition requires existence of a movement. Movement may not even exist, right? So that is the one thing, right? I think let me understand your question. Your question is that if expected value of delta n goes to g theta and variance of delta n goes to 0, then delta n is consistent for g theta, right? That is what.
No. Means if delta n is a consistent estimator, then it satisfies those two conditions.
So it may not satisfy those conditions. Because those conditions, first of all, require existence of movements, expected value of delta.
Yes. Means I consider that the moment exists.
Okay. You are saying that you want to find an example where delta n is consistent for g theta, but those conditions do not hold, right? That is what you want?
Yes, sir.
Okay. I think that is there in one of those assignments, right? Multivariate long.
Oh, okay, sir. Okay, sir. Oh.
Where expected value of delta n minus g theta whole square, I saw that doesn't go to. Is that okay?
Okay, sir. Okay.
Let's see that example that is there in the assignment. We can do that. Any other? I'll come to that. I'll show you. When we do the assignments, assignment problems, we'll discuss that. Yeah. Any other doubts from the lecture notes? No. So then, shall we go to the assignment problems? Yeah. No other doubts on lecture notes? Okay, now we can come to the assignment problems. So let me know which problem. So let me just share the screen for assignment problems. Yeah. Can you see it now?
Yes, sir.
Okay.
Yes, sir.
Now you can ask problems. If you don't have any doubts from the lecture notes anymore, then we can discuss these assignment problems. Yes, anybody? I think that example which you're talking about, let me see if I can. So this is the example, right? Let us look at a problem number 8.
Okay, sir.
X can be ID random variables with mean mu and variance sigma square. Delta n is x bar with probability 1 minus epsilon and an with probability where epsilon and n are constant satisfying epsilon n going to 0 and an epsilon going to infinity. So that delta n is consistent for estimating mu, but expected value of delta n minus mu whole square does not go to 0. Is that okay?
Yes, sir.
Actually, the idea is very simple because delta n requires rate of convergence at a much smaller rate. This ensures rate of convergence at a much faster rate. Right? So faster rate convergence may not be there, but at a smaller rate convergence may be there, and that may ensure convergence in probability. Is that okay? That is the whole
Yes,
idea.
sir.
And that is what is being done over here. I'm trying to just play around with rate of convergence with which delta n goes to this thing. So an epsilon n goes to infinity. I choose an so that this is what happens. Yes. Any doubt? You don't have any doubts in the assignment?
Sir, in the first problem,
Okay.
I have some difficulties in finding the variance of s square.
Variance of
Variance of xi minus x bar whole square.
why you need that?
So, sir, to apply CLT, do we need the variance to prove the convergence in
You will need
distribution?
for applying the CLT. You might need xi minus mu whole square, right? Not xi minus x bar whole square, because xi minus x bar whole square, if you apply that, that may be cumbersome, right? Because it would have a bivariate normal and it may be difficult.
Yes, sir, the calculation is going to be
Huh.
very complicated.
Why should you apply xi? Because central limit theorem, which you know, is for IID random variables, right?
Yes, sir.
These xi minus x bar whole squares are not IID, right?
Yes, sir.
So you cannot apply central limit theorem over here directly. However, you can apply central limit theorem to xi minus mu whole square, right? Because x1 minus mu whole square, x2 minus mu whole square, and xn minus mu whole square are IID.
Yes.
So that means you have to convert this expression into xi minus mu whole square. So that means you have to subtract here and add over here.
Then the expression becomes 1 by n minus 1 summation xi minus mu whole square minus n by n minus 1 x bar minus mu whole square.
Want me to go through the solutions? I can go through that solution if you want.
Yes, sir.
Okay. So let us look at this. S square is 1 upon n minus 1 summation xi minus x bar whole square. Is that okay? I add mu and subtract mu. So it becomes summation xi minus x bar whole square plus n times x bar minus mu whole square, right? Minus n times x bar minus mu whole square. So it becomes minus n upon n minus 1 x bar minus mu whole square, 1 upon n minus 1 summation xi minus mu whole square. Is that okay? Is that clear?
Yes, sir.
I can apply central limit theorem to these xi minus mu whole square because x1 minus mu whole square, x2 minus mu whole square are IID. Because there is a mu over here, there is no x bar over here. I cannot apply central limit theorem over here because xi minus x bars are not IID. So as such, the central limit theorem which you did for IID random variables is not applicable over here, but it is applicable over here. So that is the first thing I do. I apply central limit theorem over here. Then what does central limit theorem says? If I define Rn to be square root n, 1 upon n of mean of xi minus mu whole square. Is that okay? Minus expected value of xi minus mu whole square is how much?
Mu 2.
Sigma square, right?
Yes.
So sigma square goes in distribution to normal 0, variance of xi minus mu whole square, right?
Yes, sir.
What is the variance of xi minus mu whole square? Expected value of xi minus mu whole 4.
Mu 4 minus sigma to the power 4.
So which is same as kurtosis times sigma to power 4.
Yes, sir.
And minus expected value of x1 minus mu square whole square, which is same as sigma 4. So it becomes gamma minus 1 sigma 4, because where gamma is the kurtosis of the distribution. Is that clear?
Yes, sir. Yes.
So variance of x1 minus mu whole square is nothing but gamma minus 1 sigma to power 4. That is easy to calculate.
Mm.
So I know Rn goes to this thing, and this is related to Rn. Fine. So I'll write down this in terms of Rn. But before that, let us try to see this also. I know root n x bar minus mu goes to something, right? So I define Vn as root n x bar minus mu, which goes in distribution to, by central limit theorem, normal 0, variance of xi, which is sigma square. This is the usual central limit theorem for x bar. Is that okay?
Yes, sir.
So what you know is root n s square minus s square, which is same as root n. I write down this everything here in terms of this expression in terms of Rn and Vn. So I write down, and finally I have gotten this thing. N upon n minus 1 Rn plus root n upon n minus 1 sigma square minus root n upon n minus 1 Vn square. Is that okay? Now
Yes.
Vn goes in distribution to V. So Vn square will go to chi square on 1. But root n upon root n minus 1 goes to 0. So by
Yes.
Squaresk's lemma, this will go to 0.
Go to 0.
Right? Similarly, this will go to 0 because it is root n upon n minus 1. N upon n minus 1 goes to 1. And Rn goes in distribution to R, which is normal 0 gamma minus 1. So this goes in probability to something, and this goes in distribution to something. So by Squaresk's lemma, if you combine, everything will go in distribution. So this
Yes.
is normal 0 gamma. Right? So this is what you get. So this is the asymptotic distribution. Root n Sn square minus sigma square will go in distribution to normal 0 gamma minus 1 sigma to the power 4. Now once you have that, then Sn square minus sigma square can be written as 1 upon root n into root n of Sn square minus sigma square. 1 by root n goes to 0, and this goes in distribution to something. So by Squaresk's lemma again, this will go in probability to 0 into whatever that random variable is. So this will go in probability to 0. So Sn square minus sigma square goes in probability to 0, which is equivalent to saying that Sn square goes in probability to sigma square, which implies that Sn square is consistent for sigma square. Is that okay?
Yes, sir.
Okay. Any other doubt? Yeah. Any other doubt? But I can share that so that if those who want to note it down, let me just share it. Which one was, yeah. So this is, yeah. Any other doubts anybody has? Yes, any other doubt?
Sir, in assignment number 4, problem 16, can you discuss the last two parts?
What is this assignment number 4? Actually, assignment number 4.
Assignment number 4, yes, sir. That the heuristic argument to show that.
I don't have right now assignment 4 with me. If you tell me the assignment problem, I'll be in a position to.
So the problem is give geometric argument to show Bayes rule may not be minimax.
Bayes rule may not be.
Minimax.
That I told in the lectures. Na? Just you see, what you have to show is you can always, that example which I was showing yesterday, convex set you look at, the minimum
Yes, sir.
is unique, which is the line where x equal to y cuts, right?
Yes, sir.
And what are the Bayes rules? Bayes rules is that line, if you consider, You keep moving it and you try to see where it touches that set. Now, if you change the slope, depending on what the prior distribution is, the slope keeps changing.
Yes, sir.
That means all the points on the lower boundaries can become a tangent to some line.
That becomes base rule, all the point.
All the points in the lower boundary becomes a base rule. But
Yes, sir.
minimax among them, minimax is only one. All the rules are base, but minimax is only one, which is x equal to y line cutting, right?
Oh, yes, sir.
So base rule may not be minimax. So in fact, here there are infinitely many base rules which are not minimax. But base rule with a constant risk is minimax, right? That is what you are seeing over here. The rule over here, constant risk means R delta 0 should be same as R delta 1. And that is where y is equal to x line is cutting. Is that okay?
Yes, sir. And another is minimax rule may not be base.
Minimax rule may not be base, right? Okay. So there are many examples, right? X bar in the normal case. X bar in the normal case under squared error loss function, normal theta 1,
Yes, sir.
right? X bar is minimax, that is what we have shown,
Yes, sir.
but it cannot be base respect to any proper prior distribution. It is a generalized base, right? So geometrically also you have to think accordingly. It may not be base, it may be a limit of the base. You see, boundary may not be included, that is what I'm saying, in the convex set.
Okay, sir.
So if you want to get a concrete example I have given in the normal case, X bar is minimax, but it is not based respect to any proper prior if you consider squared error loss function. Is that okay?
Yes, sir.
Now try to think it geometrically also what is happening. So here X bar is not base, but it is a limit of base in certain sense. Yes, any other doubt anybody has? Don't have anybody, so it seems you have solved all the problems, right? I thought assignment 5 is some of the problems at least are non-trivial. But you are saying that you have solved everything, right?
No, sir, we
No, sir.
haven't gone through the
Huh?
problems yet. Uh, Actually, I haven't gone through the problems yet. Today I will try all the
So
problems.
try to
And
go through those problems.
yes, sir, today I will try.
Right, so if you have any other doubt, please feel free to ask. How are your other courses going?
Going nice, sir.
Going well? Good.
Yes, sir.
And are you people cheerful?
Not much, sir.
Eh?
Because, sir, don't get much time to read thoroughly
But
all
what do
the
you
course.
do? Home, though, what do you do? Sleep?
No, sir.
Uh,
all the pressures are simultaneously working. So that's why.
Or you have too many things to do, right? That's the reason you're not able to concentrate. That's a point you're trying to make.
Yes, sir. Also, don't get much time to read thoroughly. And also, there are quizzes every week. So that's also
Which,
one reason.
which courses there are more quizzes?
The
Statistical simulation, sir.
simulation.
Every Friday.
Simulation is
Every
Friday, right?
every Friday there is two quizzes
Yes, sir.
on average.
What are the courses for which there is a quiz?
Simulation.
Or every day there are two quizzes. Who is taking
Every
Every
week
day,
there are two.
every week.
Every week.
who is taking that course, teaching that course?
Tutika Bhat.
Dutika Vas, okay. Okay. But that course is interesting, right?
Yes, sir.
Yes, sir.
But then you are saying that you find my course to be the heaviest. I'm just taking two quiz throughout the semester.
No, sir. In that perspective, this is fine.
I'm
Sir, basically, this subject is based on theory.
What do you mean by theory? Everything is based on theory, right? You can't get away with theory, right?
No, sir. He's saying that for this course we have not done much practical things like on data analysis
Those two
kind.
quizzes are equivalent to all those weekly quizzes.
Simulation, what are the things you are doing?
In simulations, sir, there is also theory part, but there is also some coding part also where we
So,
analyze the data and see
for
visually
coding,
the results.
do you use any language or you do it in R or
In ours.
Art,
Arts.
arts.
okay? And you all are experts in R?
No,
No,
sir.
sir, trying to learn.
This is the first time you're trying to learn? Yeah, R is actually a very popular language. It is open source. That makes it more attractive. But
Yes, sir.
but then it has a inbuilt functions, right? To calculate various things, to generate random variables and all that. You don't have to write a program, right?
No, sir.
No, sir, not actually.
It directly gives you the random number.
Yes, sir. But visually seeing something
Have you
that theoretic.
have you ever statistically looked into okay, first let me ask if anybody has a doubt, then I can ask clear those doubts. Any doubt remaining for today? Okay, so let me challenge you a little bit. Now you're doing this simulation course, right? Have you ever thought, as a statistician, this black box which you are using as a R, it gives you some number. Why do you trust those numbers?
So there is a theory behind it. Means that the random number generation is not really random, but to see random pattern that is very difficult. So we can treat this actually almost random.
Huh?
All the random numbers that are generated.
If it is somebody else, some stranger who has put a name of R in his face or her face, and is giving you numbers, and you blindly accept those numbers. Have you ever thought that something could be wrong with these numbers?
Yes, sir. That those numbers may not be random.
So, if that is the case, how do you go about it as a statistician?
So we can test for randomness of the numbers given
That
to
is
me.
nothing because you are saying that it is a IID random sample, so you would test for randomness.
Yes, sir.
Test for randomness.
Yes, sir. Test for randomness that we can apply.
How do you test?
There is a
Sir,
case
there.
test.
Yes, sir.
What?
Case test.
Case test. What is that?
I mean, it tests the difference between two distributions to check if it is really random or not.
No, distribution is coming later on. Distribution would come later on. It is coming from that distribution. First of all, I'm testing whether it is really a random sample or not.
So there are turning point tests that we can use for test for randomness.
What are the tests? What are the different tests?
Turning point test is one, the non-parametric test.
What do you
So
mean?
we check that if there are too many troughs or crest, and then based on that, troughs or crest means that any point is a relative minima or relative maxima, that kind of thing. So
So basically, you try to identify some kind of a trend, right? Whether
yes,
the
sir.
data which you have got has a trend or not.
Yes, sir.
Can you imagine all kind of a trends?
No, that's not possible.
That's not possible, right? So some common trends you have to see. But for example, if you see that the sequence which you are getting is just increasing, right? That means it doesn't look like a random, right? Because first it gives the smallest one, then second one, and so on. So there is a trend, so it doesn't look like a random sample. If
Yes,
it's
sir.
increasing, then also it doesn't look like a random. It first decreases, then increases, then also there is a trend. It doesn't look like.
Yes, sir.
So you can think of all kind of possible trends.
Yes.
Now every person may think that this also reflects a trend, so everybody will come up with and each test will identify only one kind of a trend.
Yes, sir.
So what it means? That means you have to apply millions of tests to test randomness. Because every time everything gives a trend, for every trend there is a test.
Yes, sir.
Right. So this looks like a non-trivial job. Right. So how do, in real life, if I have to ask you a question, if I'm interviewing you for Goldman Sachs, how do I trust these random numbers? You're a statistician, you tell me. I don't trust R. I can trust you because you have a statistics training. So it's like this, right? That you go to a doctor with certain symptoms. Now, to begin with, what he does, either he goes for tests, all kind of infections which can take place in a body. Now, all kind of infections is unimaginable, right? So what does he do? He tries to look at the common tests, right? These are the common tests, and I apply these tests. And how those common tests have been arrived at based on the past experience, that look, these are the possible kinds of infection, but still you might have an infection like a COVID, which is a new one. And then you're in a big trouble. But in most of the situations, but COVID happens once in a lifetime, right? So that's okay. So what you do is you prepare a battery of tests. That is what happens when you go to the hospital. You go with the infection, he says that you go through these tests, right? And then we'll see. So same thing happens with random number generators. A random number generator is given to you. Somebody sets a doubt, right? Look, I have some doubt. There is some problem with this random number generator. Can you check whether it is fine or not? So what you do is you apply a battery of tests. And what are those battery of tests? Each test identifies a symptom. In this case, each test identifies a particular pattern, whether this data has that pattern or not. It is increasing, one test can be applied. Decreasing, another test can be applied, which may be similar in nature, but increasing, decreasing, then it can be applied. Now there is a concept of a run. Run means you see an increasing sequence, then decreasing, then increasing. Now if there are too many runs, that means it is increasing and then decreasing and then decreasing. That is also a trend. So what you do is you develop a battery of tests, and that is what has been done. So all these software companies spend a lot of money in preparing those battery of tests and then justifying that, look, this passes through all these tests. Now it looks like for randomness, there are about 36 tests, right? 36 to 40 tests, which are considered as standard tests for applying randomness. Now, if you want to really have some hands-on experience, you pick up any random, your PC gives you a random numbers, right? It might give you from uniform 0, 1, or Excel even gives you a uniform 0, 1. Generate 10 observations from uniform 0, 1, and test the hypothesis that it is a random sample, right? That is a one test. Second thing is, it is claiming that it is a uniform 0, 1. You test whether it is uniform 0, 1 or not. So that is a testing goodness of fit. Now you might have seen that even for testing goodness of fit, there is not a single test, because each test detects only one kind of a departure from uniformity. Right? Each test only detects one kind of a departure from uniformity. For example, I give you a random sample of 0.1, 0.2, 0.3, 0.9, equally spaced. And I claim this to be a random sample from uniform 0, 1. Now you would see that it would pass most of the tests. But here what you're seeing is a pattern. The randomness will not be passed, because there is a gap of the same length over in each of this. So the idea of getting this is, you can do a lot of statistics while doing just simple data analysis, right? While dealing with just random numbers. And you see, that is what the machine learning nowadays does, right? It generates, you have a data. For example, this problem itself is a very complex problem. That how do you test randomness? Because randomness is departure from a pattern. So how do you identify whether data has a pattern or not? Now, pattern is a very subjective concept. There could be infinitely many ways in which pattern could be violated. Machine learning, that is what you do. You have a large data. It asks the machine to learn and identify if there are certain trends, which possibly as a humans, possibly you may not be possible to foresee. I think, so I'll stop over here. So I would expect that you try to do problems, otherwise we spend a lot of time in, I don't mind doing that, but then we'll end up discussing things which may not be directly related to the course. So try to do those assignment problems. We can discuss it tomorrow and day after tomorrow. All right?
Yes, sir.
For today. Okay. Bye, everybody then.
Sir, how is your health now?
I am better. Actually, last Monday, I developed a fever. So I suspected it is a COVID. And so I had a fever for 2 days. In between, I went for a COVID test. So COVID test turned out to be negative. So it looked like it was some other infection due to which I was down. But now I'm fine. Now I'm perfectly fine. I have resumed my usual physical exercises and other things. So it's going well. And thanks for inquiring about my health. Okay, see you then. All the best. All right.
Thank you, sir.
Thank
Okay,
you,
sir.
sir.